This is EE300 Linear Circuit Analysis 2, Module 2, Video 4, Network Functions, Poles and Zeros. In this video, we'll look at some previous work on the network function. We'll work through an example circuit to explore some of the previous results and find some new results. Then we'll talk about poles and zeros and what they mean in terms of the input-output behavior of the circuit. We'll summarize and look at previews of coming attractions. So the review. We've already talked about network functions, which are the ratio of the zero-state S-domain output to the S-domain input. We have the driving point admittance and impedance, which is the ratio of the current, and the admittance being the ratio of the current to the voltage at a particular terminal pair, or the impedance being the ratio of the voltage to the current at that terminal pair. We have the transfer function, which is the ratio of an output voltage, an output signal, which in this case is a voltage, to an input signal. Again, in this case, a voltage. They don't have to be voltages. They can be currents. They can be crossed. So you can have an input current and output voltage. And we've seen that when you have an exponential input of frequency S0, there'll be an exponential of frequency S0 in the output, and the amplitude of the exponential of frequency S0 in the output will be the network function evaluated at the frequency S0 times the input amplitude. And then there's going to be the natural response terms. We also saw that we can find the differential equation, input-output differential equation, by cross-multiplying the network function terms, the denominator and numerator, with the denominator and numerator of the ratio giving us h of s, and we can interpret powers of s as orders of derivatives. So let's work through an example and explore some of these. Here's an RLC circuit where we're taking the output. It's a series RLC circuit. We're taking the output across the resistor this time. So we want to find the network function between cap V of S and cap V sub S of S. So using the voltage divider, that's going to be R over SL plus R plus 1 over SC. We clear out the compound fraction by multiplying through by SC over SC to get S R times C over S squared LC plus S times RC plus 1. And then we get a leading coefficient of 1 in the denominator in both terms, actually. And this, well, just there is no there's nothing to lead in the numerator. We can pull out the factor RC or R over L. So we get S times R over L, S squared plus S R over L plus 1 over LC. So let's find the response when we have the parameters of a 1 Henry inductor, a 7 kilo ohm resistor, and a 100 nanofarad capacitor. So when we plug those numbers in, we get 7,000 S over S squared plus 7,000 S plus 10 times 10 to the 6. And that factors, the denominator factors into S plus 2,000 times S plus 5,000. So this thing has a 0 at S equals 0, a pole at minus 2,000, and a pole at minus 5,000. So let's find the response of this to the waveform 12 e to the minus 1,000t u of t. That's a zero-state input. U of t makes it 0 for t less than 0. What's the form, first of all, of v of t? And we know the answer of what's the form. You're going to get the forced response, h of minus 1,000 times the input amplitude 12 times e to the minus 1,000t. And then you're going to have the natural frequency terms, k1 e to the minus 2,000t plus k2 e to the minus 5,000t. That didn't get formatted right, but that's e to the minus 5,000t. All times u of t, because there's no output when there's no input, volts. So we can find the parameter, we can find those quantities in this expression here. So h of minus 1,000 times 12, we plug in minus 1,000 into h of s, so we get 7,000 times minus 1,000, and minus 1,000 plus 2,000, or minus 1,000 plus 15 plus 5,000, and that turns out to be 21. You can go through and work the math out. The denominator ends up being 1 times 4,000 and 4,000. 1,000 in the numerator goes into 4,000 denominator 4 times, so 4 goes into 12, 3, and the thousands go away with the products. You've got millions actually instead of thousands. Similarly, we can find K1 and K2 just by plugging these in, evaluating. We get K1 equals 56. We get K2 equals minus 35. Standard way we've always done partial fractions. Note the nice property here. We turned a signal on at t equals 0. We're looking at the output across the resistor, and we know from looking at the circuit, the initial voltage across the capacitor is 0, and the initial current through the inductor is 0. So there's no current through the resistor. because the inductor current's 0, and so there can't be any voltage at t equals 0. And when you add up 21, minus 21 and 56 and minus 35, you get 0. So V of t will be equal to 0 at t equals 0. That's a good signal. What if we put in a constant instead? What if we just put in a 12-volt step function here? So what's going to be the form of the output then? Well, we go through the same motions. It's h of 0 now, because the frequency of the exponential is 0 to get a constant, times 12, plus k1 e to the minus 1000t, etc. Again, that should be e to the minus 1000t, not e to the minus 1000 times t. And then k2 e to the minus 2000t. So the middle term is an exponential of rate minus 1000. So what's h of 0? Well, you plug 0 in, you've got a 0, you've got s in the numerator. When you put 0 in there for s equals 0, you get 0 for the overall thing. So there's going to be no output, there's going to be no constant output at any time in response to this constant input. We put a constant input in, but we don't get a constant output. We get a constant output, but it's got an amplitude of 0, if you will. So you can think of it as the 0 at s equals 0 is blocking constant signals from showing up in the output. Even when they're in the input, they don't show up in the output. So what is the output? Well, we go back and do the partial fractions of what we have left. We plug in 12 over s for the constant 12u of t. The s's cancel, and so we just have to now evaluate that by doing partial fractions. So we get our k1 and our k2. That's going to be the final form of the answer there. And so k1 is 7,000. We plug in, we cover up the s plus 2,000 term and plug in s equals minus 2,000, and that's 28. And we do the same thing for the minus 5,000 term. So its amplitude is also is minus 28. And again, we have a voltage that's equal to 0 at t equals 0. But then we get the two exponentials add up. So you get some waveform over the duration, and then they both go to 0 as t goes to infinity. So what do these poles and zeros mean? What are they? Well, we've seen the poles before. The poles of the circuit are also known as the natural frequencies of the circuit. They're the roots of the characteristic polynomial, which is the denominator of the network function. So we find them by factoring the denominator and finding its roots. And those roots are the poles of the circuit. But for every pole in the circuit, if there's no repeated poles, then you get an exponential whose rate is the value of the pole. And we call those exponentials the modes of the circuit. And the sums of those make up the natural response of the circuit. So if you don't have any repeated poles, you're going to get an exponential for each pole, and the exponential is going to have the rate, which is the value of the pole location. If you do have a repeated pole, then your mode is going to be your exponential plus t times an exponential. The way anytime you deal with terms in the denominator with squares and cubes and the like. If you have a cube, you have a t squared times the exponential. So the poles determine which exponentials are in the output, even when they're not in the input. The pole frequencies show up as exponentials in the output, even when they're not in the input. That's the natural response of the circuit. You're always going to get that if you excite the circuit in any way. You thump it, you turn it on, you put in a step exponential of some form. You're always going to get those transients from that natural response. And those are the pole, the rates of those transients are the pole locations. Now, if you happen to drive the circuit at a pole location, then you're going to increase the order of that pole in the output. So if you had a single order pole in the circuit and you drive the pole at that frequency, you're going to get t e to the minus pole location. You're going to get t to the e to the pole location, t, etc. If you have a double pole and you drive it, you're going to get a t squared e to the minus pole location. So poles show up in the output. What are the zeros? Well, if you've got a 0 in the circuit, and it's in the, so that's the root of the numerator, and you put in a pole from this input, then the pole and the 0 are going to cancel out, and you're not going to see that frequency in the output. So zeros are exponentials in the input that don't appear in the output of the circuit. So if I've got a 0 at minus 100, and I put in e to the minus 100t, I'm not going to get e to the minus 100t in the output, because when I plug in s equals minus 100, the numerator vanishes, and I won't get any output corresponding to that term. If I want to get an output at that rate, I have to put in te to the minus. If I had a 0 at s equals minus 100, I'd have to put in te to the minus 100t. So my input has a double pole, and after I do a single pole zero cancellation, I've still got a pole in the output. How do these relate to the differential equation? Well, when you cross multiply to get the differential equation back from the network function, the terms in the denominator end up going to the left-hand side, the output side, and the terms in the numerator go to the right-hand side, the input side. The terms in the denominator polynomial, that's the characteristic polynomial of the circuit, determines the pole locations. The roots of that, set that equal to 0 and solve for the roots, and those roots are the locations of the poles. So the output side of the differential equation, which has the same coefficients as the denominator of the network function, determines where the poles are. The input side of the differential equation, which determines the numerator of the network function and vice versa, determines where the zeros are. So the poles of the roots of the denominator, they're always, that's qualified always, because again, if you've got a repeated pole or if you drive at a pole, you're going to get a t times the exponential in the output also. And that comes to the denominator, comes from the output side of the differential equation. So the poles have to do with the output. Those are the signals that are in the out. They determine the rates of the exponential that are always in the output. So the output side of the differential equation determines the natural frequencies, which determine the modes, which are always in the output. The zeros, which are the roots of the numerator, are the rates of exponentials that are never in the output, even when they're in the input. That doesn't really read right on the slide there. So even when I drive the circuit at a zero frequency, it doesn't show up with an exponential at that frequency in the output because the zero in the circuit and the pole in the input cancel each other out. And again, those come from the input side of the differential equation. So to summarize, the poles of the circuit are the rates of the exponentials that are qualified, always in shutter quotes, in the output. And they're determined by the output side of the differential equation. And the zeros of the circuit are the rates of the exponentials that are never in the output, even when they're in the input, and they're determined by the input side of the differential equation. It's a nice way to think about things. You can look at the network function, you can see the differential equation there, and you can also see where the poles and zeros come from and how the zeros have to do with the input side, the poles have to do with the output side. So what we'll do next is look at the step response and then the impulse response. And then we'll start talking about designing circuits to implement network functions. So this has been Module 2, Video 4 of EE300 Linear Circuit Analysis 2, Network Functions and Poles and Zeros.